Okay, we're ready to look at section 2. Make sure you read section 1 of your text thoroughly. Now, section 2 follows the same pattern as section 2 of chapter 1. In chapter 1 of your text, section 1, once we determine we need to find such things as spreads and centers, then we came up with a numerical way of measuring those things. Well, same thing here. In section 1 of chapter 2, we figured out that the strength of a relationship is an important indicator, and now we need to come up with a numerical way of measuring strength. And what we're going to use is this measurement called the correlation coefficient. The variable R measures the strength of a linear relationship from data. And again, I want to make sure you understand that this R only measures the strength of a linear relationship, and R comes from measuring data and not the population. So it is just a statistic, which means it will change from sample to sample. Sometimes the value R is also known more formally as Pearson's correlation coefficient. So R is just a number between -1 and 1. Now, what do these numbers mean? So it's any real number between -1 and 1 are the values that R can take on. So what would happen if R, for example, is -1, one of the extremes? Well, here's what the data would look like if that was the case. I would take my first order pair and I would get this value. Then I would take it again and I would get this again, 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 again. And here's a result of taking data from a relationship between x and y where r equals -1. In other words, it's perfect. There is no variation. You give me a value of x, I can tell you exactly what the value of y is. And in this case, the slope is negative, so r will be a -1. You can only guess then what r of equaling 1 will be. If r equals 1, then what kind of picture do we have? We would have exact opposite, except now it's a positive correlation. Again, there will be no variation. You give me the value of x, I can tell you exactly what the value of y will be. So r equals -1, perfectly negatively correlated. R equals 1 is perfectly positively correlated. Now, as we get away from -1 and 1 and go towards 0, that's where we get this scattering effect. And here are values that would produce 0. The first graph here is the classical case of 0, where you have a scattering. But again, notice here, as x increases, what can you tell me of what's occurring to y? What's happening to y on average as x increases? And what you can see is as x increases, y is going up, is going down, but the trend stays pretty much flat. On average, it's not doing anything. So really what's going on here, as x increases, what's happening to y on average? The answer is nothing. But that's actually very informative as well. That means that really x cannot really explain why y changes the way it does. So we say there is no association between x and y. Again, when we say there's an association, it means that knowing something about one variable lets us know something about the other variable. That's what's important here. Really, that's what the end result is. We want to know more about the response variable, again, the variable of interest, and we're going to do so by knowing something about the x variable. It will give us a clue as to why y behaves the way it does, or at least even allows us to predict a particular value of y, another possibility. Here also, again, you can see that there's a very strong relationship. As a matter of fact, it's very, very strong, but R produces 0. Why? Because R measures only a linear relationship, nothing else. This next picture will also produce a value of 0. Notice as R well, sorry, as x changes, what's happening to y on average? The answer, nothing. Again, this lets us know that x and y are not associated. Because really what I'm trying to say is, as x changes, does that tell me something about how y is about to change? And in this case, it says that y doesn't change at all as x changes. It stays fixed. So to reiterate, this last graph and the first graph say there is no association between x and y, because as x changes, on average, I can't tell you what's happening to y, or it's staying steady on average. So therefore, there's no new information. While this second one says there is a very strong association between x and y, but it also produces an r value of 0 because clearly this association is not linear. And R only measures a linear association. Here's what I'd like to do next. I want to just show you what R is. And then next we'll show you how to calculate R. But first what I'd like you to do is go to your browser and type in this web address, as I'm going to do the same. So go ahead and stop this for the moment and type this into your web browser. Okay, now I want to show you again what this equation is. I don't mean to scare you, but here's the equation. Now, you might be wondering, am I going to have to calculate this by hand? No, we're going to let the computer do this. This will be very cumbersome to do by hand. But what I want you to know is what's it doing. Now, here's what it says to do. Take every single order pair, x1, y1, and do the following. Subtract the average of all the data values from each data value, order pair, and divide by the standard deviation. So this is sample standard deviation, this is sample mean. So basically, if you look closely, you got to do this to every single order pair until you're done. But what does this produce? Well, actually look at this closely. It's the measurement minus its mean divided by standard deviation. It's a z-score. It's like a pseudo little mini z-score for your sample. So in reality, what we're doing is we're taking the product of z-scores. Now, here, before we get into this applet that we're going to look at, what I want you to remember is something. If a number is to the left of the mean, right, that means its z-score is negative. In other words, if the number is smaller than its mean, the number is negative. If this number's measurement is larger than the mean, then the z-score is positive. Same thing for the y. So if it's below the average, it will be negative. If it's above the average, it will be positive. So here, what we potentially have, we're taking product of each x and y z-scores. So if they're both positive, it'll come out positive. If they're both negative, it will come out negative. Now keep that in mind, and let's go to the applet. So this is the website that you should have logged into, and I'm going to now scroll a little bit down, and you see that one of the entries here is statistical applets, so I'm going to select that. And what I want to play with right now is this applet called two variable calculator. Notice correlation and regression. So this one right here, so I'm going to click on it. And then it'll take a second here to load. Now let's pick a particular data set. I'm going to choose this one, the second one, value of income of NBA teams. Let's click on it, and I'm going to choose correlation and regression. Now when I do that, again, I could see some values. The mean of the x's is 264. The mean of the y's is 6.131. You can look in your book to see what the what these numbers actually mean in terms of the units. This happens to be the regression line, the line of best fit. But right now I'm getting a correlation of 0.2107. Okay, very closer to 0 than to 1. So this is telling me that the association is positive because this number is positive. but it's also close to 0, which is telling me the association is not that strong. So let's look at the scatter plot now. And I get the following. So I'm going to scroll down here a little further. Actually, I'm moving my entire window. And you'll notice that at the bottom says show least squares regression line. I'm going to do that. Click. And then the most important part is show mean of x and y lines. Do this. Now, why do I need to show the mean of x and y? Because remember what we did earlier. I mentioned that the z-scores here will come up positive or negative depending if my values are to the left or to the right of the means, respectively. Okay, so now let's look at the graph again. Here's the mean of the x's right here. This is the mean of the y's, and you'll notice by doing so we split the quadrant into 4 regions. Now, for example, if I look at the x values here, to the right here, all these x values produce a z-score that's positive. If I now look at the y mean, anything above this line will produce a z-score that's positive. So all these points, for example, are to the right of this line, so the x's are all positive, and it's above this line, so all the y's are positive, so a positive times a positive produces a positive product. Similarly, everything here on this other side is negative, so this is to the left of the mean of the x's, so all the x values will be negative, and then below this line all the y values will be having a negative z-score, so a negative times a negative will be positive. So this third quadrant also produces positive z-scores. But if I look at the quadrants 2 and 3, the exact opposite is true. Here, for example, the x values will be all negative, but because they're sitting in the second quadrant, all the y values have still positive z-scores. Positive times a negative produces a negative. So now, if you look at the formula again, what's happening is these numbers are negative, these numbers are negative, numbers here are positive, positive. When you start adding up positive and negatives, what happens? You get cancellation taking place. So what's happening is if we have a strong linear trend, all of a sudden most of the ordered pairs will lie in either this quadrant and this quadrant, very few on here and here, which again lets us know that it's a stronger relationship linearly. Let's pick another ordered pair, another data set. I'll choose this third one here. And again, I'm going to click on the scatter plot. Now again, do you feel there's a strong association or a weak association? Now if I look at all my scatter points, I can see that most of them lie on either this quadrant or this quadrant. But again, diagonal quadrants produce the same type of, in this case, negative number, negative product. These two quadrants against first and third produce positive values. So there's hardly, when I actually sum things up, there's hardly any opposition to these values, so I'm expecting a very large R value or a strong R value. But again, there's also a lot of separation, so it's not going to be too strong, but there should be strong. So now let's look at data. Nope. Correlation and regression. Sorry. And what's my R value? Notice it is 0.778, much stronger than before. It would have been stronger if the dots lined up in a, closer to the trend line or the regression line, which is this right here, that red line you see there. I'm going to pick another data value, another data set, gas mileage versus logs. Well, let's see. No, this one. Neuron response to tones and monkey calls. That should be interesting. So I'm going to do my scatter plot. And again, what do you think? How strong is the association? One thing I see is, again, I have a lot of scattered all over the place. So I can see there's a positive trend, but it's very, very loose. And again, notice I have a lot of points here and a lot of points here opposing each other. These points on first and third quadrants are opposing those on the second and the fourth. So I'm guessing this is going to be a very low R value. I'm going to guess 0.21. Let's guess. Let's see what happens. So I'm going to click on Correlation and Regression tab. 0.6386. So there, you see, I don't know what I'm talking about. The only thing I could say is there must be just a lot of more values here. So the fact there's a lot of values produced a much higher than I expected, really, R value. So there's still a lot of points here, a lot of points here, but not enough to counteract. Boy, I still can't believe that. So at least that gives you some feel of how what this number means. Next, we're going to look at how to do this on Excel.